Yeah, okay, perfect. So thank you very much. First, thanks for the invitation, and thanks everyone for coming. So as Lucas just said, I work at CERN. I work on what we call the platform infrastructure teams. We have a few teams doing cloud-native deployments and machine learning platforms. I'm also in the TOC, as you mentioned. Today, I will actually do a small demo at the end, but what I would like to talk to you about is sustainability and AI. AI is the big topic of the day. It's the same where I work, but it's not in sustainability necessarily of environmental sustainability. It's more the sustainability that Sarah was talking about, which is making things work long term. We make decisions now that we'll have to be able to maintain over the coming years. Also, I like space, so it's always good to have a talk where I can show rockets. But the reason I show this is because whenever I think about sustainability, there's something that comes to my mind, which is the picture from Eagle when just before the moon landing. And there's this amazing podcast by the BBC called 13 Minutes to the Moon. And it has the communications of all this phase from the moment that Eagle starts leaving orbit to landing, all the communication with command module. And it shows you that after all these years of preparation, they actually had to make a decision last minute, which was to change the landing site because it didn't look like what they were expecting. And they had to push forward, and they had to move a few hundred meters, and they ended up with a few seconds of fuel before they had to abort the mission. So they actually landed, but it was very close. And this is often what we end up having to deal with. We made decisions that then we have to justify later. There's a very similar example from a Swiss person, Bertrand Piccard, that went around the world in a balloon. And he had, you can see here on the bottom, these gas bottles. When he landed, he had less than half a gas bottle left. And they actually, while they were crossing the Atlantic, they realized they won't have enough fuel to finalize the trip unless the wind quadruples in speed, which is pretty wishful thinking, but we all do this constantly. I wish that GPUs maybe will become a lot less expensive, and then all of this will become much easier. But this is wishful thinking. So we should prepare for maybe it won't happen. So I work at CERN. We have this big particle collider, the Large Hadron Collider, and we accelerate protons to very close to the speed of light. We make them, smash them against each other in these big caverns with large detectors. And in the end, this is just a gigantic camera that produces a lot of data, So if we look at a slightly different picture of the detector, we see that we are producing 40 million pictures or collisions per second, taking 40 million pictures, producing 1 petabyte a second. This is not something we can deal with. So what we do, we filter them. And we know that we can trash most of it, but there are things that we don't know we have to select, and we would like to keep them all, but we can't because of technology. So typically this is done by hardware at the start, and then it goes through different software filters. If we look at what's coming up next year for this detector, it will be a large 5,000 node cluster, actually a Kubernetes cluster, managing 30,000 applications to work on all this data. Now, my colleague Giuseppe from Atlas, he presented this back in Salt Lake at KubeCon, and he explained what's coming. And this is just to give you an idea. So we have these 40 million pictures, 40 megahertz on the left, and then you filter them, and you go to 100 kilohertz, which is 300 gigabytes per second, and this is what we are going through the first filtering farm with this 5,000 node cluster, and then we reduce it to 10 gigabytes that we store and analyze later. Now, the high luminosity Large Hadron Collider is just about to come up in a couple of years, and will increase from 300 gigabytes to 5 terabytes a second, and from 10 gigabytes to 50 gigabytes per second. This is constantly happening. Physicists really push us to have better luminosity, more data, and we have to cope with it. Now, there's a problem, which is we don't make money out of particles. So we increase the number of particles, but we don't increase the budget with it. So we have to find some alternatives to deal with this. Now, there's this thing called Moore's Law that I'm sure many of you have heard, or all of you, which said since the 70s, kind of empirical evidence showed that the number of transistors is doubling every 2 years. This was great, because we could just rely on the increase in the technology to cope with these needs that kept increasing as well. Now, there's a trend that it seems like it's flattening, and because of different reasons, but it means that people are looking at different ways of doing things. And this is GPU, AI, workloads, all these things. And we all have to deal with this. If we look at the plan for the LHC, this is 2030, that will have this upgrade with this that I just mentioned. The next decade doesn't look any better. Like, it will keep increasing. So today's AI, next time will be something different. But we have to learn how to deal with this to make it sustainable. Now, GPUs are amazing. We all love them. They have bad things, which is mostly the price, and also the watts. Like, if you see how much an Ampere generation GPU, the A100, will take, it's between 250 and 400 watts per card. If it's fully interconnected, it takes more. If we look at the Hopper architectures, we see already 700 watts per GPU. Now, if we look at Blackwell, which is the new one, then it gets to 1 kilowatt per GPU. And not only that, they started focusing on the new workloads, things like LLMs, where the floating point precision, the things like double precision performance are not so important. But again, we have to make things sustainable. We have a lot of workloads that really rely on double precision. So you cannot just buy these GPUs, change all your data center to accommodate these GPUs and forget about the past. It doesn't work like this, unfortunately. So we have to accommodate. We have to learn how to buy these GPUs, but accommodate the old things. So maybe we have to split the GPUs. We have to learn how to deal with it and accommodate all these things. So the technology that we've been developing the last couple of years, specifically in the CNCF, is really what helps us not have to throw everything we've done for 10 years and start from scratch, which would be pretty much madness. If we don't do anything, though, this is how a rack looks at CERN. Pretty sad. Like, we are putting 25 kilowatts in this rack. We have 6 quads there with 8 GPUs each, and we are taking just a small fraction of the power we could. So we are spending a lot of money and not making enough out of it. This is not sustainable. We won't make it with GPUs this way. The reasons are very much human. We have different teams at CERN. So, for example, we have the notebooks team. They want their GPUs. They want their cluster. They want dedicated resources because they want their service to be successful. We have the machine learning team doing training, serving. They want the same. They want their GPUs. They want dedicated resources. They want to guarantee that their service is successful. And then we have like the HPC workloads that don't even use Kubernetes. They're still using GPUs in a different way, deploying them in a different way. So how do we do this? If we keep people isolated in this way, we won't optimize the overall goals. So how do we go from that to what we want, which is to maximize the usage of resources? And this is the picture on the right, where you see we're basically filling the rack with the workloads we want. And this is where the community really has helped in the last few years. So everyone realized if we go with AI, we don't want to start from scratch. We need to change the ecosystem to accommodate these workloads. And this is how it looks. And I will do a demo of a cluster that we just put up with a couple of GPUs, where this is how it looks. We don't no longer isolate people. We have these central components. In this case, it's a component called Q that helps us with scheduling. And we developed, as a community, all this functionality we need to be efficient. And this has things like quotas, queues, priority and preemption, gang scheduling, all the things we need to be successful in AI. And we give control to the infrastructure people to decide where these workloads should run. It's no longer the users or the service managers deciding this. We can evaluate what's the best use of resources in this case. In most cases, it will be on premises for us, but in many cases, it will also be bursting to the public cloud. And this is really where it's key. So we did this advanced functionality, and we need also to understand how to accommodate different workloads to the existing expensive resources. The community has also come up with a lot more things. The second thing, I talked about infrastructure. Extremely important is observability. And we have Casper here, so I have to mention observability. We need to know in detail what the workloads are supposed to be doing and how they are performing to make the best decisions. So OpenCost is an example from the landscape as well that focuses on cost, but I actually started incorporating also things like watts. We want to have an idea of what's the cost of each workload, events per dollar, events per watt. Also, we want to be able to also introduce carbon into the picture. It is important. When we apply for grants from funding agencies, they will ask us for the carbon footprint. So we need to be able to report on this. Again, the community came forward. There's a tool from an initiative called Sustainable Computing that's called Kepler that allows us to predict what's the carbon consumption of the different workloads. And this is a very nice, kind of simple example, but very nice way where we submit the workloads on premises, we can calculate the model based on the sources of power we have internally, and it's the same for the public cloud. We can decide which region we use, also based on the power sources in that area. So, just before I go to the next slide, I talked about infrastructure. There's one thing that is even harder than solving the technical challenges, which is the human part. And Sarah talked very well about this all. It's the same in everyone's jobs, I'm sure. So we give people flexible infrastructure with all these layers, and then all this fancy stuff. They can do training, they can do serving, they can do everything. Do you know what's the single most common request we got from users internally at CERN? Just shout something. Functionality, protocols, access patterns. Give it a go. Web servers, could be. Storage, for sure, yeah. So the single most important one is SSH. Now, if you've been doing containers, you SSH to nodes as rarely as possible, just to debug really tricky things. But for our users, this is how they work. This is how their scripts are made. And it doesn't matter how fancy we make the infrastructure, if we don't get the users to buy in, all of this will never be used properly, and we will fail. So we started looking at all these boxes. We knew we could do all these things: continuous integration, MPI, training, serving. We can do all the stats, all the benchmarks, and it's amazing. We go to interactive, and we have the new generations. They like notebooks, VS Code. But a lot of our users, if it doesn't allow me to SSH, I don't use it. And that's a no-go. So this is why I will jump to my quick demo, which I will try to show you this. So this is a live cluster at CERN. You can see the global monitoring. So again, this is just turned on, so the usage is not huge yet, but it has a couple of hundred GPUs. And then you can see the different users people are waking up, so you see some things popping up here. Again, I mentioned that monitoring is critical. So if we go to the detailed usage, we can see someone woke up here. They're actually doing quite well. They're so this is Jakob, I know this person. He's doing close to 100%, so very nice user. We have others that are like this, but we have a lot that are mostly idle, and you can see what the problem is. We need to learn how to share these resources to make the best of them. So what I will do, I'll go to my own area, and I'm a nice user, so I have my own workload here doing really well, and I'm very close to 2/3 of usage. I have one node with workload with 4 GPUs being requested. You can see I'm taking 1.5 kilowatts, so pretty nicely. Now, I will show you how this works. So if I do get pod, you will know about this. So you see I'm just burning the GPU, so it's actually not doing anything useful. But this is how submission works. So this is all they have to do. We don't have a lot of YAML engineers, but this is YAML that they can handle. And you can see that I just say which kind of services I want, the image I want to run. In this case, I'm not doing much. I will ask for 4 GPUs of this kind. This is all they have to do. This is extremely important that it's this easy. So if I create it, I will see it takes a couple of seconds to start. It's initializing. All right, so it's running. I will log into it. kubectl exec, everyone knows about this. We're all happy with it. And if it works, it's even better, yes. So, and then I'm in my container. I can see I have my 4 GPUs. These are H100s, 400 watts potential each, and I can see the usage, and I monitor. Everything looks great. So this is great, but this is, when we demo this, is like, what's this kubectl, kubectl? I don't know how you call it, but I don't like it. I want SSH. So we came up with this project called Container SSH. Actually, it was the community came up, and CERN got behind it as well. So we have 2 maintainers in-house. And I want to SSH to my container. And this is possible. You can create dynamically the workload, or you can just log into a workload that already exists. So you can see here that suddenly I got an additional bash shell in my container that comes from the session. And I can use it exactly in the same way. I just do VDSMI. I will have the same. Pretty simple, but actually extremely effective into getting people to buy in. Second part I said is that we need to be able to share GPUs. So this is what you need. If you look at this example here, this is my full GPU. I ask for 4 GPUs in this line here. All I change is to use this MIG, which is a multi-instance GPU from NVIDIA. You say you want a fraction of a GPU with 47 gigabytes. So what I will do is I will exit this. I will create this half GPU. And again, this is as far as they want to go with YAML. And we'll wait a couple of seconds. It's there. So then I log in. And if I do NVDSMI, you will see that I see the full H100 here, but I'm actually only allowed to use a MIG device that has 47 gigabytes of memory. So suddenly, even if my workload is not that efficient, I can sneak in other workloads in the same GPU. So I'm increasing the overall efficiency. Now, the last bit I want to show is, and I'll just do a top here, is code. And this is also very important. If we look at VS Code, this is something that was the second most wanted request, which is I want to log into my workloads using code. And this is just using, because we use Kubernetes and it's so present everywhere, if I go to, I just installed an extension in my VS Code. I have my 3 sessions that I just created before. And all I have to do as a user, I say attach Visual Studio Code. It will launch a new code session. And it takes a couple of seconds. And of course, I didn't update something. But it will take a couple of seconds to give me a session in the same way I had SSH. I can now just use code. And the environment feels like home. So I can just go here. And again, if I do NVDSMI, I have my 4 GPUs because it's the full session. And if I go back to my demo, you see a bunch of node processes that are from the extensions that just logged in. So very simple demo, but I hope it kind of shows the potential of all this and what we've built and how essential it is to make sure this works in this easy way to make sure that AI and the new workloads continue to be sustainable. So thank you very much.